Good morning, good afternoon, and good evening, everyone, depending on where you are. First of all, thank you so much for joining us today for this third seminar in our quarterly seminar series. This seminar is organized by ECSPrecip, which is a Students and Early Career Subcommittee of AGU's Hydrology Section Precipitation Technical Committee. Before we move to seminar, I would like to take just a couple of minutes to introduce ourselves. I'm Shruti Upadhyaya, Assistant Professor in Indian Institute of Technology, Hyderabad. I'm the chair of the subcommittee along with Dr. Yunjin Lee. She's the deputy chair. We are an amazing team of more than 20 students and early careers from various academic institutes and research labs. We bring in young scientists interested in different aspects of precipitation related research with a goal to better connect with them, providing them opportunities for networking, professional development, and recognition. So the ECS subcommittee is striving to facilitate an open, inclusive, as well as a collaborative environment for students and young scientists in the field. For those who are new here, we have two series of bi-weekly newsletters called Precip Folks and Science Highlights. So if you have any latest publications related to precipitation, you can actually submit using the Google form on our webpage. We will advertise them in our Science Highlight newsletters. Also, if you are not on our mailing list, please subscribe to our mailing list. You can find all the details on our webpage. If not, one of us will share the links in chat. Lastly, I would like to mention that we are organizing another in-person or mostly a hybrid meeting every year at AGU Fall Meeting. This is again a panel discussion mainly for networking with both all the precipitation scientists in the field. So if you are attending AGU Fall Meeting this year, please attend it. It is open to all and details will be on our webpage soon. So with this, I would like to thank you again for joining and just wanted to highlight that this session will be recorded and will be posted on our website. Now I'll hand over to our moderators, Amy and Mochi. Thank you, everyone.
Thank you, Shruti. My name is Mochi Liao. I'm a postdoctoral research scientist at UIUC. This seminar provides an introduction to various precipitation products, including satellites, field experiments, and models. Today, we invited three experts in these fields. Hi, Amy, would you like to introduce yourself and the speakers today?
Yeah, so my name is Amy Matlin-Dixon, and I'm a PhD student at the University of Oklahoma. Our three speakers today are going to be Dr. Lynn McMurdie, Dr. Joe Turk, and Dr. Kerry Emanuel. Without further ado, we can go ahead and kick it off. We'll get started. So we're covering again the three perspectives of field, satellite, and numerical weather prediction precipitation. And so Dr. Lynn McMurdie will be our first speaker. She is a research professor at the University of Washington Department of Atmospheric Sciences. She has participated in or led several recent field campaigns aimed at understanding precipitation processes. From our theme highlighting field, satellite, and numerical weather prediction precipitation, she will be covering the field perspective. She will be talking about various field campaigns, their instrumentation, and how to go about using the data from these efforts. Dr. McMurdie, the floor is yours.
Thank you very much. Just give me a second here to get things lined up. Share. Okay, and then hang on, I will find, there we go. Okay, thank you so much for inviting me to be here. I'm really excited to tell you about my favorite topic, and that's precipitation and fieldwork and precipitation. So I will include lots of photos taken in the field, and I'll try to label them whenever appropriate. And this one was from a field campaign in Argentina called Relámpago. So I'm sure I don't have to convince you all that a field campaign measuring precipitation is not just a bunch of rain gauges that you place anywhere you feel like it to measure rain. You need far more sophisticated instrumentation than this to understand processes that contribute to that precipitation and to explain why it's distributed the way it's distributed, and to help predict and help our models to be able to predict how the precipitation is distributed. One type, I had pictures of rain gauges, but one kind of key instrumentation that you might want to have on the ground is called a parseval. And a picture of it is shown here in the corner of this picture. And it has like a laser beam that measures particles as they're falling across that beam, and it can actually measure the sizes of your particles, either liquid or even frozen. So knowing the distribution of the sizes of the particles is an important aspect to understand the processes that contributed to that rainfall. You often like to co-locate that with gauges, as shown here in this particular installation. But it does take power, and they don't take a lot of power. You can actually use a solar panel here. I did want to point out that often to do accurate measurements of surface precipitation, you want to take into account wind, because your wind can blow across and make the particles blow across your gauge instead of into it. So often, if you have an ability to put in a windscreen, that's a great addition. Measuring frozen precipitation is far more challenging. One, it usually often occurs in remote locations, such as mountainous regions. And you have to do a typical tipping bucket gauge like I had in the previous pictures can't measure frozen precipitation because it's not a drop. So you usually use a rain gauge that's called a pluvio. It's a weighing gauge. It weighs the content of the container, and you have to put this glycol mixture in there to essentially melt your frozen precipitation, so you get the liquid water equivalent of the falling precipitation. That requires you have to go out and empty it once in a while, which is what this person has just did and is now restocking it with glycol. This is an installation we did in a very remote location. We had to mount our pluvio on a trailer because the snowpack actually got up to the bottom here. This is like 6 feet in the air. Snow-tell sites, which are permanent installations in mountains, do include a pluvio type gauge that's put in a very, very tall structure, because these things can get also buried with snowfall. And then those sites also can measure snow depth. You don't see it here because it's under the snow, but a thing is called a snow pill to measure the weight of the snowpack. So often when you measure precipitation in a snowing environment, and especially in the mountains, you want to know the nature of the actual storage, and not just how much fell as it's falling, but then it compacts down, and how much water do we have sitting on the ground waiting for this summer season to melt and become our water supply. So snow-tell sites are to do that. But we also collect precipitation data by flying in the clouds themselves as the precipitation particles are being formed. And this is some aircraft. This is all the P3 aircraft that I'm just recently was involved with. And the actual instruments in this case are mounted to the wings. Outside the two propellers here, so there's like a artist rendition, and they're measuring as we fly in the clouds. Particles go into these probes, and there's instrumentation in there or to measure the particle sizes, the distribution again of the particles, inferring also other types of probes. This one's called a hot wire boom. Here it measures the liquid water that's in the cloud, or total water content from which, if you had both liquid and ice, you can come up with the ice water content. So these are measuring in situ, so you see the processes of how the precipitation is formed, and then if you have fly over where there's gauges on the ground, you see what falls out. So I'm going to say there's, yeah, thank you. So also to measure, one of the key things for most field campaigns is we use remote sensing type instrumentation, most commonly radars. And you can either fly a radar on a plane, as shown here on the ER2. There's radars hiding in these pods on the side, or you have them installed on the ground. The bigger ones called the ones that are that measure in the S-band range for a radar, they're fairly large, so you have to have a good location to put it, and you have to be able to move it. It takes 4 sea containers to move this radar to a site. And then, but if you use smaller wavelength bands like X-band or KU and KA, you can actually put them on the backs of trucks and drive to your location as long as you have permission to use those radars at that location. So there's been a lot of field campaigns over the years. I couldn't possibly list them all. The types of instrumentation, the observational strategies, etc., all really depend on the goals of that particular field campaign. How much funding they have, and how accessible and availability of sites. Luckily, most of the recent ones practice open science, where all the data are publicly accessible and downloadable, free of charge. And I just threw in a bunch of logos from some recent field campaigns. And then on this slide, I made a list of just ones that I could think of, and I'm sure I missed the ones that it's your favorite, but if you're interested, I'm going to pause here a little bit and you can do a quick screenshot, all these links, so you can get access to the data that was collected from these different field campaigns. This group is all focused on tropical or convective type field campaigns. They took place like in the Great Plains in Oklahoma and Iowa, Argentina, Taiwan. The Precip one, it was a really great data set that's been collected there. And I think it's just now available for anybody to use. CPEX was last summer, I should say 22 recently. So it's still also data's coming. So hopefully you got a shot of that. I can give you slides. These are being recorded, so someone can get this later. And then this is a list of winter-focused field campaigns. The Olympics field campaign, Snowy Sail Splash, just completed. That's more of a hydrology one. And Impacts is the last one. So I'm going to actually show you some data that we collected during the Olympics field campaign here, listed here, and the Impacts one. These are the two that I was very heavily involved with or led myself. So I'm start with the Olympics field campaign. Again, if you want to take a screenshot, and these are all valid links of where you can get the data. This is some data collected by a Parsifal, like I highlighted at the beginning. And what we have is a time series of data. So each of these plots on the left is a time for a period of a very intense rainfall event that occurred 12th, 13th November 2015. And the top here is a time series of the precipitation rate at different stations. So the stations here are shown on this map. And this is a type of field campaign where we were at one location and we put a lot of instrumentation either on the ground, and we actually had aircraft as well, and a lot of radars to really focus on the processes that contribute to precipitation in an orographic area, and how the precipitation processes change over the ocean, and then as they encounter land and higher terrain. And that's kind of what this is demonstrating. So this very heavy rain event often could be considered an atmospheric river type event. And at the top plot here is the rainfall rates. And you'll notice at first when the ramp up is happening, all the different stations are kind of the same amount of rainfall, and then they kind of spread apart. So during that atmospheric river event, when it's really the heart of the transportation of high water vapor content, the stations that are on the forward windward slopes, they're the ones that are raining the most, and the ones down the valley, actually it kind of stopped raining very much. It even dropped back down close to zero. So a lot of enhancement. And what kind of droplets are doing that? It's the small ones. So that's what this parcel can tell me, is showing the distribution of drop sizes with time. Lots of these small ones. So we have ones that are less than millimeters. This is the size of our raindrops, are less than a millimeter. And they just, all of a sudden, we got a lot of those small guys. And what's interesting when you look at the contribution of the different raindrops, it was the small ones that really added to the total rainfall that's being collected by the gauges. The small droplets that are occurring, which is actually the warm rain processes, are part of what enhances the precipitation on the windward slopes. So an example of the radar from a ground radar, so this was the end pole one, there's pictures on here, shows that we, instead of just looking in a sweeping view, you can look in a vertical view. What is the vertical structure of the clouds? And that's where you start really understanding better what's going on. This is called the bright band, where the ice, it melts and becomes very bright to a radar and then falls as rain. At this early time, we have, you also have radar yield velocity. So are the particles moving towards or away from the radar? And at the beginning, when that wasn't very heavy rain, we had a outflow, offshore flow at the low levels. So this green arrow shows the flow is going away from the mountains. It's only the arrow over the top that's going towards it. But then later, we had all the air going towards the mountains, and that's what the air is being lifted and creating those small drops. So that's written in this article here, is Zagrodnik et al. You can see more if you want when you go there. So I'm running close to out of time, and I'm going to switch over to my other field campaign called Impacts, Investigative Microphysics and Precipitation in Atlantic Coast Threatening Snowstorms. And this is a very different nature snows field campaign, one that's aircraft based. And the benefit of this is that we can go to where the storms are. At Olympics, we only could measure storms that happen over the Washington state. Thankfully, it's a very rainy place in the wintertime, so we got lots of storms. But here we were kind of chasing snowstorms. And so this graph on the bottom here is our flight tracks from just this last winter. We went from Minnesota, we were in Maine and Canada, down off the Carolina coast, over New England. We went everywhere. And the key thing that we did is flew two aircraft in coordination with one another. The top aircraft that's well above the clouds, the ER2, it had the remote sensing instruments. So it had the radars on the aircraft and the radiometers on the aircraft, looking at the structure of the clouds and precipitation. And underneath it, the P3 measured properties of the clouds, the microphysics of the clouds. We did also have ground instrumentation and ground radars, but they were concentrated in New England. So whenever we happened to be in New England, we flew over those sites as well. So this is an example event that we flew over Chicago in 2022. Also impacts we had 3 seasons of observations. And this event, it's snowing pretty darn heavily at Chicago, and they're not very happy with us because they're trying to figure out what to do with all the planes that can't land in Chicago. They're like lining up, but we're flying in the middle of all of them. This is a view of radar reflectivity from all the NEXRAD operational radars. But on the right, this is what we saw from the aircraft. I accidentally went forward, but that doesn't matter. W band, Ka band, and Ku band here. And I have plotted on top of it the HER model to show you that we are going across kind of an elevated frontal zone. And we see that we have an enhancement of reflectivity at the end, where we are flying through what I would call a snow band, a big broad snow band. So what does the EP3 look like there? So we have the P3s flying along at this level about 3.5 kilometers. This is actually what we call a skin pate of the P3, and it intersects this intense region of reflectivity. And the microphysics there is fairly interesting. We have pictures of what we saw, very big aggregates of snow particles. The mean diameter increases, the number of small particles decreases, ice water content increases in that snow band. Outside, much smaller particles, much more bigger small particles, and a little more dense as well. So not big open dendrites. So that's a very cool thing to learn. And I just had to show you another example of one of our probes. This is a different event, but what's really cool is that we have beautiful pictures of the shapes and sizes of the particles. And when we were in a snow band, we saw these beautiful dendrites. And notice how the dendrites have little dots on them. They're super cool liquid water is adhering and freezing right onto the particles. And when we're outside the snow bands, the particles are very pristine looking. So I'm advertising the fact that you can learn a lot more about impacts because we have a data workshop in a month. Please contact me. We'll get you on the list and you can learn much more about a lot of data that I didn't show you and hear from the instrument PIs exactly how to work with this data and how to access it. These links I show here are links to the impacts data and to the Olympics data. And we also have what's called field catalogs, which are accessible now. You can click on these and go right there and learn a lot more. So with that, I should end because I'm a little past my 15 minutes. The references and a few more shots of the views of what we do in the field. And I can end my slideshow. So be happy. I'll answer questions, I guess, at the end. Thank you.
Thank you, Dr. McMurdie. So yes, we'll take all the questions at the end. So feel free to just post questions in the chat if you have any. Otherwise, we'll open it up at the end for questions for all the speakers. So just moving on here, our next speaker is Dr. Joe Turk. Dr. Joe Turk is a member of the Radar Science and Engineering section at JPL. His overall primary interest is atmospheric, passive, and active remote sensing related to clouds and precipitation, and the observations needed to improve their representation in weather and climate models. Prior to JPL, he worked for the Naval Research Laboratory's Marine Meteorology Division. He has been active in NASA's TRMM and GPM science teams, serving as an editor for the AMS Journal of Hydrometeorology, and is active in the organization of the CGMS WMO International Precipitation Working Group since its inception. He will be covering the satellite theme in this seminar and will inspire us by sharing his perspective of existing challenges to satellite remote sensing of precipitation that require further investigation. So Dr. Turk, the floor is yours.
Okay, thank you. Can first check everybody can see my screen and hear my voice. So thanks again, Amy, for having me speak, and thank you, Lynn, for the good introduction. It's been a pleasure. I think I worked with you on one field campaign. It was Olympics. A few pictures here of some satellite data in the lower right here, current instrument on the International Space Station, just to show that not everything has to be up at high orbiting spacecraft. So just a little bit about myself. I'm from a very snowy part of the world. I grew up in the Upper Peninsula of Michigan. So when you ask how you got interested in this field, well, snow was a big part of my daily life. But I come from an engineering background. I got interested more in radio wave propagation and went to work in industry for a while. And I'm showing this because a lot of you maybe are still uncertain about what you want to do, how you want to use the knowledge you're gaining. And I was unsure of that myself until well into my 20s, late 20s even. When I went back to get my PhD, fortunately I had a great advisor there and studied radar meteorology. As Amy said, I got more interested in the science end after that. So I just thought I'd throw that up there. So I'm going to talk a little bit about remotely sensed precipitation estimation. I don't have a lot of quantitative detail like Lynn had. I'll just give you some feel for this, and then Dr. Emanuel can pick up the model theme. But so I thought I would tie in what I'm saying with numerical models, because actually remotely sense observations of precip from satellites. And I'm assuming you're familiar with how a radar works and hopefully how a passive microwave radiometer works. I'll just explain that briefly. But they really have a symbiotic relationship with numerical models. The satellite observations are very good. They're obviously influenced by the precipitation, your bouncing signals off of rain, but they really don't know anything about the environment that the rain forms, right? The temperature and moisture, very little knowledge of that. And I'll show how the current products like iMerge and GPROF, some of you are familiar with, they have to deal with that. But on the other hand, models are very good at providing the environmental state that exists when it condenses water to make rain. But the model itself is not perfect. It may put the rain in the wrong place at the wrong time or at the wrong intensity or structure. So in general, most satellite algorithms have to rely in one way upon a model, and most models use satellite data for assessing their precip. So there's always been this symbiosis between the two in a big picture sense. Let's see if I can go next slide. So just a few other details when you actually start looking at satellite data. When you're in space, remember satellites are looking down from onto the clouds and the precipitation's at the bottom. So you have to, the sensors have to deal with the precipitation in between before they can estimate that near surface precip, which is really what hydrologists want. They don't, particularly want the rain at 5 kilometers above the surface. And satellites are intermittent, as we all know. They have an orbit pattern. How long, was it before the previous satellite overflew? Did you miss an extreme event because it happened? Things like that. So there's always these sampling issues you have to deal with. And satellite instruments it's like your hearing, right? There's a fundamental lower limit to what they can detect in terms of intensity. I'll show an example. And current resolutions are really limited in their capability to resolve the kilometer or even sub-kilometer scale nature of convective precip. And who knows what technology will bring in the future, but that's the way it is nowadays. So if you're not familiar with satellite passive microwave radiometers, it's really a study in contrast, right? And if you've all probably seen a thermal infrared sensor picture before, this is actually a picture from the JPL Visitor Museum, and that's actually my wife right there in the lower right. And you can see her forehead is warm in this color representation, and her nose is cold, right? I mean, so it's all just really thermal. It's a thermal picture. Something's warm and cold. Well, and again, this is in the infrared. If we just were to make that same picture in the microwave, that's really what we're doing, right? We're just switching the frequency to a much longer wavelength. And in this band, the constituents on the Earth, they both emit radiation, just Planck's law, and they reflect or scatter radiation. And this is at one particular channel, 19 gigahertz. It's a common frequency used and by many passive microwave radiometers. And you can see this is Canada, obviously up here. And you can see some surfaces are warm, like the reddish colors, like the land and so forth. And then some surfaces are cold, like water. But precip, you can see it right here where my mouse is moving, hopefully, that tends to emit radiation quite well at this frequency, so it starts to warm. For example, inland water bodies right here, they tend to emit and scatter a little bit, so they're kind of somewhere in between. Now, if we switch to a higher frequency on this radiometer, this is up at an 89 gigahertz channel, which is much, 3 millimeter wavelength. Things are a little bit different. You can see precipitation scatters even more, and so it starts to get quite cold. These temperatures are down near 120, 160 Kelvin. And water vapor in clouds are still pretty small at that wavelength, so they tend to emit even more, and so they start to warm up even more. So this is the big thing that you do with passive microwave radiometry. It's a study in contrast. How do you pick out the precip against the background surface, which can in some cases look like precip itself, as you see hopefully in this example. And this is a busy slide, but there's a takeaway to it. On the left, I've just simply shown the DPR radar, which GPM's current operating radar. It's the dual frequency precipitation radar. When I've simply plotted here is anywhere that rainfall detected a non-zero rain, and I plotted in a space that's the 2 meter air temperature, so that's temperature on the x-axis, and then the total column water vapor on the y, which is a measure of moisture. So these are the environmental variables I was referring to earlier that the satellite doesn't really know about, It, you know, it can sense the precip, but it doesn't really have a way to tell you what the 2-meter air temperature is, for example. But you can see the space in which the GPM satellite, in this case, can sense. You know, this is where the regimes, you might call, of which it can detect precip. And over here on the right, it's the same picture, except that I took cases where the DPR said it didn't rain, but another instrument called CloudSat, which I won't explain, but it's a better detector of precip, where it said it was raining. And so what is this? This is the regime that the GPM misses. And you can see it's really the snow and the drizzle, right? Temperatures down here below freezing and some of this light rain. This is nothing new. I mean, people have shown this, but kind of a nice depiction of what, you know, this idea of detectability of just some things that current instruments can't see. But the estimation of precip from these data, the inverse problem is really very ill posed, right? You've got over on the left here, you've got many, many factors influencing the precipitation state. This is just a few kind of things I've shown. And then you've got the satellite flying over it, which provides relatively few pieces of independent information about this precipitation state. And you're trying to tell what the surface precip is. So it's really very ill posed. And furthermore, the observations, as I mentioned, are influenced by the precipitation itself, but also these other quantities like the temperature and the moisture and things like that. So one way this is typically handled is in current algorithms anyhow, is using a Bayesian approach, and it's all based on creating prior data. So you have what you might build over here on the left is a large prior data set, could be many millions, could be many, many millions, you know, a large prior data set that encompasses all the possible regimes that you think your satellite will sample, and you have to include the precipitating one and the non-precipitating. I mean, non-precipitating observation is a zero rainfall rate is a perfectly valid answer. So, and typically in this big data set you might create, you would have the precipitation structure and the associated brightness temperatures, of course, at the same frequencies as the satellite instrument. And then the job of the inversion is to pick ones that are congruent to your observations, right? So you want to somehow extract the profiles where the brightness temperature are similar to the observed TV. And I put similar in quotes because that's where the magic really is. And, you know, so you might in this case find two profiles that are similar, and then you can, this is very crude. I mean, the whole idea of the estimation and its variability is difficult to quantify because precip isn't Gaussian or anything like that. But this gives you an idea of how an algorithm might work in an efficient way. And in fact, this is basically how the GPROF algorithm, which NASA uses, it operates in a big picture sense. But as I said, the factors that influence this brightness temperature are many, many others than the desired ones, like the surface temperature. You know, the radiometer is looking down at the ground, which, as I showed in that picture from Canada, can be sometime cold, it can be sometime warm, you know, depending if there's snow on it, or if it's wet, or if the soil is damp, or the soil is dry. And so to some extent, you can constrain this a little bit. It's not as desperate as I said in that little cartoon I showed earlier. You might rely on a model. That's going back to my first point. Numerical models are quite good at modeling temperature, for example, and water vapor. So you might use that as to help you with like a first guess, right? You might pick candidates that have similar temperatures and water vapor conditions to what existed at the time of your satellite, or you might pick a candidate with similar Earth surface conditions. Things like this you might know, and you might take into account the fact that a lot of these conditions are somehow correlated with each other as well. So it is really less pieces of information than you need. And as I said, this is what's currently done inside of the current algorithm called GPROF that GPM uses, and that's what feeds iMerge, which is what many, many of us use. But as you've probably been thinking, you know, these results are only dependent upon the realism and the representativeness of that large data set that I showed you earlier. So that's really the secret is in making that very representative. Just as one example, and this is my last slide, actually, if I have a wrap-up one. Let's say, for example, you had a 2-channel microwave radiometer that's being used to estimate precip. So here, the OBS stands for observation. So there's T1 and T2. And you've got two surfaces, right, that you're trying to pick an answer from. And the surface emissivity at these two channels is plotted on the X and Y, right? And surface A has a mean of sigma-1 and a variance of sigma-2 for the two emissivities. There, and you can see there's really no correlation between these two. Surface B has the identical mean for sigma-1 and sigma-2, but you can see the emissivity is somehow quite correlated. If I didn't know anything about this, if I didn't know that the surface was correlated, I would, these two answers right here, profile 1 and profile 2, would be identically valid. I wouldn't know which one to pick. But if I knew the surface emissivity was correlated, like I'm showing here in surface B, I can disqualify one of them right away. So you can do things like this, and this is a very simple way of describing, how these algorithms, search their prior databases for candidate answers. But it gives you an idea of how you can exploit natural correlations in certain things to help reduce the dimensionality of the problem. So just will wrap up my last slide. In my opinion, not my employer's, I think future global satellite precipitation data products are going to be a big fusion of data, various instruments and platforms, models, gauges, ground radars, at a fast update. And it'll take a lot of work. And it may not come from necessarily the big federal government agencies we're used to dealing with, right? Maybe industry can move a lot faster. And in fact, as some of you know, there are many Earth observations now being provided in a small and CubeSat-sized form from weather companies, and even NOAA with their next, after JPSS, will be looking at that also. And how are these all going to work together? I mean, that could be a title. I could give a whole separate talk on that. And as I mentioned, this representative training data sets, the AI techniques can do this much more efficiently than, say, like these kind of Bayesian sort of brute force techniques. Can we use, TRIM and GPM go back 25 years now? That's a pretty nice representative training data set. Maybe some ideas there. And the last thing is in the validation. I just, right now we're used to using a lot of radar data and gauges over the United States, and it's a very good data set, but it only samples the regimes that exist in the United States in the surrounding waters. So how do we really start to better validate our satellites and models more globally, outside of these regimes? And that's, I think, an open question. Anyhow, that's what I prepared. I just kind of wanted to give you a little sort of flavor for how some of these algorithms work, and maybe where the satellites are going, observations, and I'll turn it back to Amy and to Dr. Emanuel. Thank you.
Thank you very much, Dr. Turk. In the interest of time, we'll move on to our next speaker, Dr. Kerry Emanuel. And I just want to remind everyone to go ahead and put your questions in the chat for the end. All right, so moving on here. So Dr. Kerry Emanuel is an emeritus professor of atmospheric science at MIT, specializing in physics of the tropical atmosphere, including tropical cyclones. He will be covering the numerical weather prediction modeling of precipitation theme of this seminar series by talking about a tropical cyclone precipitation data set from an advancing downscale model. Dr. Emanuel, the floor is yours.
Thank you very much, Amy. Very nice to be with all of you here. Amy, can you see my opening slide all right? Just want to make sure.
Yes, we can see it.
Okay,
perfectly.
all right. So I'm going to present a very kind of specialized data set on precipitation for you today. One of the things that we're interested about when we're interested about precipitation are extreme events, because they have large social impact. And the same extreme events provide challenges for all kinds of different ways to observe them, whether it's rain gauges, radars, satellite, and so forth. So we have to do the best we can. And one of the other ways that we can try to estimate precipitation is from models. So I want to tell you about one such effort to do that for the case of tropical cyclone precipitation. I'm speaking to you from a fishing village on the coast of Maine where we're about to experience a tropical cyclone, Hurricane Lee. Why is hurricane rain important? I probably don't need to spend a lot of time convincing you that it is. But if you want to look at some rather grisly statistics, if you look actually all around the world, but this is for hurricanes in the United States, almost all the mortality and a great deal of the damage is actually done by water, even though hurricanes are thought of as windstorms, and indeed they are. Most of the problems actually have to do with water, salt water from storm surges, fresh water from torrential rains causing inland flooding. And this is the big problem with hurricanes. It's not so much wind. So we're very interested in hurricane precipitation and whether that might change over time, for example. So how do we go about estimating long-term hurricane flood risk? So there are two sort of problems with precipitation. There's the immediate forecast problem, which is terribly important, but also for estimating long-term flood risk. This is terribly important too, because it informs the design of infrastructure. It sets insurance premiums, or should anyway, and so forth. So we're very interested in long-term risk. And risk is dominated almost always for almost anything by extreme events. Now, I've been very interested in using physics to assess weather risks in general, and in this case, hurricane risks. The traditional way of doing it is to look at historical statistics of the event. And in fact, almost all insurance premiums today and other instruments of risk are based upon statistical analysis of past events. But that's very problematic. First of all, the records are usually not nearly long enough to capture the extreme events that tend to dominate a really long-term record. Like 100-year events, we don't usually have 100 years of records. Also, the history turns out not to be a very good guide to what's happening right now because of climate change that's already occurred. So what we do in my group is we begin with something we consider reliable, which are global records of, let's call it, coarse scale climate. These are the sorts of things you get from reanalysis, like ERA5. They're on a scale of maybe 100 kilometers or so. Now they have very fine time resolution, like an hour or so. And if you're not interested in very small scale events like convection, but the larger scale synoptic environments, these are our best shot at creating them, and they can go back, nowadays, some of them go back 100 years or so, but reliably back 50 years. So we start with those, we cull from these data sets the key statistics that we know from decades of research control the generation, movement, and intensity of tropical cyclones. And use those statistics, we bootstrap these statistically to create potentially unlimited synthetic time series of the environmental, the large-scale environmental variables that are known to be important for hurricanes. So we're basically trying to create very large data sets, if you will, for hurricane-relevant environments, not yet the storms themselves. That comes in the next step. We use these statistics to derive specialized, very, very high resolution physical, as opposed to statistical models of hurricane genesis, track, and intensity, and also, of course, models of the hurricane wind field, and more recently, models of the hurricane rain field. The rain is, like the intensity, also calculated deterministically, that is actually using the known equations that govern these things. It's a very complicated process. It's been developed over a few decades now. You don't really believe it unless you can evaluate it against real data. And that's something that we've done, but frankly, we haven't done enough of because it's very, very labor intensive. And it's also very interesting. And it's something that some of you might get interested in. And if that's the case, I'll provide you the means to do so. Once you've done that, you can apply exactly the same method to the output of climate models if you're interested in the climate of the past, the distant past, or climate of the future. So to jump right to the results of doing this, we often try to focus our attention in particular places. So when we create these synthetic tracks, we filter them to focus on a particular area. We can do this anywhere in the world. You're seeing a map of the top 100 out of a set of 2,000 synthetic tropical cyclones that pass within a certain distance of the city of Kyoto in Japan. From downscaled from, in this case, a climate model run over the 20th century, but this is for the period 1981 to 2000. So the little black dots are the genesis points. The color coding is a measure of the wind speed, the maximum wind speed to storm at every point of its lifetime. And then, of course, it goes on until it's declared no longer a cyclone. All these points by design converge on Kyoto. We're just simply throwing away the ones that don't create a chart like this. And this is just a eye candy test or eyeball test. The magenta tracks are historical tracks now, real tracks that have been superimposed on this. Getting to rain, I'm going to show you the storm plot of the storm total rainfall from one of these synthetic tracks, just one out of a set of many thousand, that happens to be something, a rather Harvey-like event. If you remember Hurricane Harvey of 2017, which affected South Texas, that storm came in from the Gulf, stalled over the coastal region, and then went back out to sea. That black line is the track of the center of a synthetic event that kind of behaved the same way. And you can see this is a very extreme event. It created more than a meter of rainfall in some places. If you think that's extreme, well, there are places in Taiwan that have had more than 2 meters of rainfall from typhoons. Now you can do that repeating this over very large numbers of storms, and in this case over 8 climate models, okay, and use all the statistics you get from that to create a map like this, which is the 100-year, the rain associated with a 100-year event at the centroid of each county in the United States over the period 1984 to 2014. And you can see by looking at this map that, not surprisingly, most of the high rainfall is in Florida and the Gulf Coast. And you also, if you have good eyes, might see a bit of a maximum along the ridge of the Appalachian Mountains. Okay, now using the same color scale and the same 8 climate models, we're going to go forward to the end of this century, 2070 to 2100, under a fairly high but not extreme emission scenario, SSP 7.0. And you can see just by comparing these two that it's a really big increase in rainfall in the places that experience rainfall from these storms. So this is these are the kinds of maps you can make from such data, but what we're really interested in is more detailed and critical comparison of what we get from these synthetic events to what we observe. So let me just jump quickly to giving you access to these data sets. So what I'm making available to you right now, if you are interested, is a set of 21,000 storms that affect US East Coast and Gulf, downscaled from ERA 5 reanalyses from 1979 to 2021. There's quite a few events, not climate models in this case, but reanalysis. They're filtered so that at landfall, they have wind speeds of at least 62 knots, so basically hurricanes. Unfortunately, this is a drawback we hope to conquer someday, but you'd have to have access to the MATLAB program to work with this particular data set. Apologies for that, and you'll need about 250 megabytes of disk space. So I hope you can access this by a screenshot or by looking at this when it's made available afterwards. But here's basically an FTP repository where you can get everything you need for this particular data set. And just follow the instructions that come with it. It's pretty simple. A lot of people have used it over a long time, so the bugs are out of the, I hope, the guidance for using it. And you will find that for rain, which is the subject of this little symposium we're having, there's a particular MATLAB script which I've named here, which you will find most useful. If you are so moved and you've succeeded in going through these steps, you can contact me and I can give you access to the climate model output I referred to from 8 models. It's a long story. You'll have to sign a non-redistribution agreement not to redistribute those data sets, but that shouldn't be much of a limitation. So that's all I have. And here are some key references to these synthetic track generators. Okay, thank you.
Thank you all for the great talks, and now we can start with the questions. We have one question from Pfizer to Dr. Turk. You mentioned the recently launched tomorrow at the end of your presentation, a huge achievement, and I was wondering if you had any insights or comments on the planned accessibility of said private sector satellite products like this for future public use. Perhaps not as real-time products, but it would be great to have access to additional data sets like this in our work.
Yeah, that's a great question. I started to respond to it in the chat, so I'll just continue my response here. I can give you some hints on that. I mean, there's 2 current instruments on the International Space Station now called COVR, which is called the Compact Ocean Wind Vector Radiometer, and TEMPEST, which stands for, I forgot the acronym, but it's a high frequency radiometer. And those are available now on NASA's PODAC, their physical oceanography Earth data site. All you need is an Earth data account, which is free, and you can go to PODAC and get that. That goes back to 2022. The 4 tropic satellites operated by the PI from MIT, Dr. Bill Blackwell, and his great team have been, I heard, operating very good. And so I imagine that data will be released publicly in coming, I don't know, months or something, or I'm not sure. But that will be, I think, a great opportunity to compare tropics data from against the GPM precipitation data. And as far as tomorrow.io goes, that's a private company. Many of the people actually that work there worked at NASA, so we know the instruments are going to be great, right? So, but those are a suite of radiometers, Ka-band radiometers. It's a private company. I can't speak for what they'll do in terms of public release of data, but I would assume there would be some mechanism for that through, one of NASA's commercial data buys or something like that. But I have no authority in that matter. So my best advice is to, look ahead to tropics data in the coming months, and the data you can get now from COVR and TEMPEST. I hope that helps.
Thank you. There's another question which is already answered, but I think it's worthy to be said to the public. So there's a question from Shuki that said, I have 2 questions for Dr. Lynn McMurdie. He says, are these data set quality control? And can you provide some broader overview for those people who work on other regions of the world can take advantage of such field campaign data sets?
Yeah, these are great questions. I'm glad to be able to speak to the large audience. Yes, any data that's put in a permanent repository has to be quality controlled. NASA provided data sets. They usually give us 6 months to do the QC. I have to tell you, we're a little light on this last batch from the impacts, but because we're up against 6 months right about now and not all the data's there. but certainly stuff in the past that wasn't, just in 2023. Those data are there, quality controlled the best and often they get updated even later as we learn new things that we didn't take into account and add improvements. So the links that I provided, they should be all quality controlled data. Speaking to the broader audience, worldwide, I can see the problem. Like anybody from a different country wouldn't necessarily know the names of field campaigns, wouldn't know what to search for. Like, I know there's field campaigns somewhere. Where are they? What are they called? And so I think there's some effort. I talked to a colleague at a late conference I went to this summer. She's part of kind of an international precipitation group. Her name is Jagmir Denmar. I can't remember her last name exactly, but she's trying to put together like a master list. Please give me this data, links so people who are interested in a little description of what kind of field campaign it was and such. So, and there's certainly of my list, I was very US centric, or at least the ones I knew that were sponsored by US, but there's a lot of European based field campaigns out there, Asian ones, all kinds. So should be a big effort to try to consolidate that so that the information could be in one location, and then it depends on what your interests are, it should be able to access. But I know the US policy is like if it's public funds was used to run that field campaign, that data is required to be public to anybody who wants it. So I hope that answers the question. I see that Jackson Tan has his or her hand up. So I don't know.
Yes, thank you.
Yeah.
Yeah. Jackson, would you like to speak your question?
Yeah, sure. So this is a question to all speakers. So, we have 3 talks with very different topics, different domains. But for the longest time, at least at NASA, we talked about something called level 4, which Joe sort of alluded to, which is the idea that we take satellites and combine them with models in a very intricate way, more than just like reanalysis. So why is it that we are still lacking a level 4 product? Like, is there merit in putting everything together? But is it the case that we lack the knowledge or the resources or the coordination, or is it just not a good idea to put everything in one basket? If that makes sense.
I think we're all running away from that question as fast as possible. I'm gonna let Joe take that one. That's what more.
It's a good point. I think let's set aside the real-time aspects of that for a minute. Because just getting data in a real-time fashion from all those sources is a heroic effort in itself. So let's just assume they were all magically available to a product developer. So that makes answering your question a little easier. I'm not a model expert, so I may hurt myself in what I'm going to say here or anything on that aspect. But at least from the satellites and gauges, there's a huge quality control effort that has to go through these things. So let's set that aside. Let's assume everything is perfectly quality controlled and everything adheres to standards in baseline, in a baseline product you might have from the radar or gauge or something like that. I could see where the fact that the different instruments, for example, are sensing different parts of the precipitation. Some are measuring, like radiometers sense precip up in the sky. So gauges measure some on the ground, right? Radar scan, maybe they do a better job of getting at the precip at the surface than the radars do in space. So I think there still would be mechanistic things about putting them all together that probably are going to be just take a lot of trial and error, I think. And that as I was alluding to in my talk, as Jackson, private companies are starting to do this already, and they can work faster than the federal sector. That's not a criticism. That's just the way it is. I think we just need to. That's why I said it's going to take a lot of work. I think it's going to take a work from a large community to try and find the way that these pieces put together. It's not as easy as just merging products at different times and locations.
I'm much too old to be a big enthusiast of AI, but I think this is a perfect problem for AI. I really do. We've got all this disparate data. sources, if you have long enough records and you have some kind of ground truth, what you regard as ground truth, I think this is a really wonderful problem for somebody gifted in that to try to do. And then, of course, as Joe Turk mentioned, you have the problem of getting the data available in real time. That's always going to be with us. But I'm optimistic that AI could probably bring this problem forward quickly if you can solve the availability problem.
Okay, right. Thank you.
Thank you. There's one final question from Lisa, Dr. Kerry Emanuel. The observations and models are deeply intertwined. Satellite algorithms use models to help drive their retrievals, and models need observations to improve. From model perspective, what do you think observations should provide more or better to improve models?
I'll keep a narrow focus to my answer to your question and just talk about precipitation. One of the things we noticed in trying to figure out how well we were doing with these synthetic tracks, we tried to do comparisons to both rain gauge data and radar data, just ground-based radar data. We didn't use satellite data so far, but just those two sources, when you get up to the higher wind speeds, begin to disagree with each other a lot. And so we have a problem that how are you going to optimize or evaluate numerical weather forecast of rain or a long-term risk assessment if you're talking of events where things like rain gauges start to have problems in high winds and radar starts to have problems, for example, losing power, to take one simple example. So for me, this is a big problem. Those are the events you're really interested in from a forecasting and a long-term risk perspective. And it's in those events where the current observational techniques are not working well. And so that's where we need help. That's not really an answer to your question because I don't know how we're going to do that, but that's where we should focus some attention.
I may add a little bit to that. So a lot of the purposes of these field campaign and data is to kind of address helping improve models. For example, a lot of our data collected impacts, because we have so much microphysics information and we relate it to radar information, we can improve microphysics parameterizations. So it may not be at the hurricane force winds events that we were going in, but we went in quite a variety of storms. So we sampled just a wide variety of types of events and the manifestations of microphysics. So a lot of field campaign data, depending on the purpose of it, piece by piece can help improve algorithms, and then you test algorithms broader than what the field campaign itself was aimed for. So the data types, many of those campaigns I showed you can be applied to improving both satellite remote sensing and modeling of precipitation. Someday it'll help.
Thank you. I think our time is done, and a huge thanks to everyone in the Zoom call today. And yeah, I think that's the end of this seminar. Thank you, everyone.
Thank you too. Thank you for inviting us. Appreciate it.
Thank you.
So I enjoyed it. Thank you very much.
Likewise.
Yeah. See you, Joe. See you, Kerry.
Bye, everybody.
Bye-bye.
Bye.
See some of you next week.
Yeah. Good luck.